What exactly happens when we rotate points in 3D space? If, for example, we have just a single vertex as represented by this small orange sphere, and we then rotate it anti-clockwise from this initial position to this position, what calculations are involved and are matrices required or not? For an intuitive understanding, let's start by considering the vertex as represented by this yellow position vector, and then use its initial horizontal and vertical position values to calculate its new rotational position by using the geometrical relationships of right-angled triangle trigonometry. Let's rotate the initial vertical position value of the orange vertex, represented by this blue vector, by the angle of rotation being applied to the vertex, so that's from here to here. We also need to rotate its initial horizontal position value by the same angle. Notice that although initially there was only a single vertical component and a single horizontal component, we now have two vertical components and two horizontal components, which together represent the new vertex position. At this stage, even without any calculations, we can clearly see that we already have two visual vector representations of the vertex's new position. These two vectors are these two vectors. These four vectors are these four vectors, which are the four we'll be calculating to determine the vertex's new position just here, as follows. To calculate each of the two smaller components, we use cosine theta equals adjacent divided by hypotenuse for the horizontal value, and sine theta equals opposite divided by hypotenuse for the vertical value. The two values we know are the angle, which is 47 degrees, and the hypotenuse, which is equal to the initial horizontal position value. We calculate each of the two larger components in the same manner, with the angle of rotation remaining the same, but this time the hypotenuse is equal to the initial vertical position. Next, we subtract the two horizontal values to get the x value, and add the two vertical values to get the y value. We can run a simple test program using OpenGL, for example, by passing the sine and cosine values of a continuously changing angle to the vertex shader, like this, and then within the vertex shader, multiply those values by the horizontal and vertical vertex position attributes, like this. We can also simulate animating the model's orange vector like this, which allows us to verify the results in the console window. Finally, notice how this x value vector and this y value vector together represent what can be referred to as the new x-axis. Likewise, this new x value vector and this new y value vector represent the new y-axis. And there we have it, a geometric understanding of how to rotate points around the z-axis. In the next tutorial, we'll be taking a quick look at how to rotate around the x and y axis in the same manner, and then in the third tutorial we'll look at how to combine axes. We'll also be looking at matrices, scaling and translations, and further examples as we progress. Please don't forget to subscribe if you'd like to see more. Cheerio for now.